Concrete fractures at very low stress when subjected to pulling forces, yet under compressive loads, it can withstand massive crushing forces. To bridge this physical gap, embedded steel reinforcement is required to carry tensile loads across the inevitable cracks. Mastering the composite behavior of these two materials is the focus of postgraduate structural engineering. Because the material relies on physical cracking to function, it degrades continuously under load, rendering simple linear mathematical models obsolete. The Leonhardt shear beam experiment is a physical benchmark. The schematic details a simply supported beam, loaded vertically at two top points. Classical linear elastic models assume an idealized response, predicting a smooth, unbroken deflection curve. That assumption disappears the moment concrete exceeds its tensile capacity. Traditional hand calculations cannot map the structural response once this initial cracking phase begins. In the Leonhardt beam, this leads to a diagonal shear failure. Failing to predict an abrupt failure mechanism threatens structural serviceability and compromises human safety. Preventing shear collapse requires transitioning to a mathematical framework that tracks local degradation incrementally. The mathematical solution begins with a fracture plastic constitutive model. Instead of dropping to zero stress instantly upon cracking, real concrete transfers tension across the widening fissure through aggregate interlock, an effect known as tension softening. This graph illustrates the exponential tension softening curve. The shaded area beneath the line represents fracture energy, the measurable amount of energy dissipated per unit of cracked area. In finite element analysis, refining the digital grid can cause the math to artificially reduce computed strength. To prevent this mesh dependency, the crack band theory scales the crack opening over a characteristic element length, converting it into a mathematically stable strain. Smearing the opening over a defined band ensures the dissipated energy remains constant, whether the software uses a fine or coarse grid. With the concrete modeled, longitudinal reinforcement must be placed. Discrete, one-dimensional steel truss elements are mapped directly into the two-dimensional concrete grid. The bar snaps into place independently of the concrete nodes. The interaction between the two materials is governed by an explicit bond-slip law, defining the shear stress and relative slip. This mechanical friction dictates realistic crack spacing and ensures the intact concrete between cracks continues to carry residual tensile force. Modeling the steel and concrete as separate entities is insufficient. Predicting ultimate capacity requires calculating their friction and strain compatibility. At every load step, the simulation solves the global equilibrium equation, governed heavily by the tangent stiffness. That tangent stiffness decreases continually as the concrete fractures. The software applies the total load in small increments, utilizing iterative procedures like the Newton-Raphson method to restore balance within each step. Engineers can instruct the solver to apply a fixed amount of force or a fixed amount of physical deformation. When simulating concrete, displacement control must be used. Applying pure force causes the mathematical calculations to collapse at the exact moment the physical structure peaks. Displacement control forces the equations to track the deformation even as the member loses load-carrying capacity. By calculating equilibrium incrementally through displacement, the model maps the entire life cycle of a failure. In the post-processing phase, numerical output translates into visual engineering data. The principal strain visualization reveals a highly localized contour band, expanding diagonally from the load application point down to the support base. This chart plots the load versus displacement. The response moves up the initial stiff incline, rounds the peak capacity, and drops sharply down the post-peak softening branch. Tracing that descending curve exposes the limited ductility of a shear failure. The nonlinear finite element simulation computes the exact mechanism that linear equations missed. The algorithms required to fracture the Leonhardt beam are identical to those used for massive infrastructure and critical load-bearing systems. Safety requires pairing objective fracture theory with rigorous bond-slip mathematics. Nonlinear finite element analysis provides the computational bridge between theoretical design assumptions and physical reality.